Welcome back. In this session, we are going to study about anti-reflection coating. Reflections that appear on ordinary lens without any anti-reflection coating. Reflections that do not appear on anti-reflecting lenses. It's one of the application of interference that using interference technique we can avoid unnecessary reflection from lens and glass surface. When light passes through a lens, a part of it is lost due to reflection. For example, the light passes from air to glass. About 4% of the light is reflected and lost. So if you are providing a thin layer of anti-reflecting coating on lens and glass surface, such loss can be minimized. So let's study in detail about anti-reflection coating. Anti-reflection coating, it is a method of eliminating reflection, utilizing the phase change and dependence of reflectivity on index of refraction. Let's see what are the material that is used, what should be the refractive index of the material and how it is done, and so on. Generally, transparent materials are used as coat material such as silicon oxide, magnesium fluoride, etc. Coating lens and glass surface with anti-reflecting material should not destroy the purpose of the material. That is why we use transparent materials. The refractive index of the coat is given by refractive index mu c is equal to root of mu g according to ample condition. That is, the refractive index must be greater than air and must be less than glass. Generally, this thin layer coating of anti-reflecting material is done by thin film technique, namely physical vapor deposition or chemical vapor deposition. Let's see how we do the chemical vapor deposition. So in chemical vapor deposition, what we have is a substrate over which we need to provide anti-reflecting layer. So the substrate is kept in a reaction chamber. It is heated, and into the reaction chamber we introduce gases, reactant gases, which will react together to form solid coating on the heated substrate, and the waste gas is removed out of the reaction chamber. So this is how the chemical vapor deposition is done, or anti-reflecting layer is provided on lens and glass surface. Mechanism of anti-reflection coating. Anti-reflection coating creates double reflecting surface which gives two reflected waves. These two reflected waves will be out of phase, cancelling all reflections. Let's see how it is done. So this is the anti-reflecting layer which is provided on glass surface. So we have two interfaces. One is the air coat interface and the second interface is coat glass interface. So light falling on the first interface is reflected and it is transmitted. The transmitted one is again reflected from the second interface and emerge out, which will be out of phase with the light reflected from the first interface. Therefore, it will be cancelling or it will be undergoing destructive interference. We know interference is redistribution of energy. So due to reflection, no energy is lost or the energy is being transmitted. Let's find the thickness of the film so that the surface will appear anti-reflecting. Now when you choose a coat material, the refractive index criteria is the refractive index of the coat must be greater than air, and when you compare coat index with the refractive index of the glass, it must be less than that of glass. So when you compare the first interface, it is a rarer denser interface, and when you compare the second interface, it is again a rarer denser interface. So while calculating the path difference between the light reflected from the first interface and light reflected from the second interface, no need of taking into account the path change or phase change that happens to the light due to reflection from a rarer denser interface, because both surfaces are rarer denser interface. From theory of interference of thin film, path difference is equal to 2 mu t cos r. Over here, path difference is equal to 2 mu c t cos r. For destructive interference to happen, equate the path difference to the general condition for minimum, that is 2 mu c t cos r is equal to 2n plus 1 lambda by 2 to find the minimum thickness of the film. And for normal incidence, we can write 2 mu c t is equal to lambda by 2, n equal to 0 for minimum thickness and r being 0 for normal incident. The equation takes the form 2 mu c t equal to lambda by 2 or t equal to lambda by 4 mu c. We know mu c is equal to root of mu g. So if you provide on lens and glass surface a thin layer of coating of anti-reflecting material with thickness correspond to this value, then the surface will appear anti-reflecting.